Okay, so Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Um, okay, so we are now in the third class, right? Yeah. So we have touched a little bit on the introduction to refinery. It's We went very quickly, and also we touched a little bit on the optimization, so mathematical optimization. So those two classes were more like to as an introduction, because the assumption is that you should have followed these two courses, refinery and optimization, before you could then do this class, which is refinery optimization. But nonetheless, um, it's done, yeah. If there is anything that you don't understand, just let us know, um, and then don't hesitate to just ask questions. And so far, I don't or we don't receive any questions from any of you, so I'm assuming that all of you are, yeah, doing okay, right? So now we move on to chapter three, which is then the so we dig a little bit deeper on the refinery itself, and this is also going to be the introduction for your project. So we have now three students and two lecturers. Yeah, I mean, we should have like at least three or five, even, I would say, projects to be submitted. Um, the So for today's class, it's more on we dig a little bit deeper on the one of the unit operations. We'll see, because today we have only like a 2 hour session. We dig a little bit on the unit, one unit, which is I think I would say like hydrocracking, because it's very simple to understand and also to model. I'll Because I'm going to introduce you as well to one of the process simulator software, which is Symmetry. By now, I hope that because we have shared at least about 2 weeks ago on how to connect, on how to access Symmetry from UTP. So we will by now, I hope that you have access to that. um, and So we will use that, and then we will use that to yeah, for your projects and then your exercise as well, and also to keep you with a skill to do process simulation, especially for chemical plants and refinery. Okay. Main references, you could look into this, and then I think here I would and, pen. So I would encourage you to go to this one, for modeling and optimization. So the case study, yeah. So today we'll be discussing about the symmetry and then the case study. So case study that you will do is that you will use well, we call it refinery modeling and simulation with surrogate model for optimization. So it's too many buzzwords. So basically, refinery modeling is that you make from your plant. If you have a plant, yeah, if you have a plant, you make a model. Or you can use you can use symmetry to make a model for that, and then or you can go to the examples of symmetry. I will show you later on, if you don't have any. But I strongly encourage, because all of you are working people, so I strongly encourage you to get your own plant data, because by the end of the by the end of this course, then you can do something, and then you can then show something to your boss that you could do, in fact, optimize your own plant, not just theoretical, which nobody's going to use it. So if you have your own plant data, which I encourage you to have one, please get that. If not, then we will then use symmetry, and where to take examples for that, if you don't want to get if you I mean, just to make it quick, yeah, because we have only like a few weeks to go. um, and then once we make the model, we will then use that to simulate that. So that model, we will use it as a plant. Yeah, so it becomes the plant, and then that plant obviously will have to run it. That we have to simulate that. We have to simulate that to generate data. To generate data. So if you have your own plant, and then your first job is then done, right? Because the first job is that you get the model. So I will write it down here. So we have you have a plant data. So you have now if you don't have any, then you make a model. This then like a surrogate model. And then if you don't have
Sorry,
any, then you have to start.
Zafan,
Yeah.
are you sharing your screen?
Yes, I am sharing the screen. I guess if you don't see it, then okay, then please
I
let me
don't
know.
see it. I don't see it.
Yeah, okay.
The others could see.
Well, you should have told me this right from the beginning. Oh yeah,
Sorry.
yeah. Um,
Okay, now I can see.
no, I'm really suspicious with it, and I'm talking alone or I'm again, yeah. If there is something wrong, just let me know quickly, because then okay, where were we? Now I don't remember. Uh, um, okay, so the case study. So today is to introduce case study for your project, and then to how to use symmetry for that. Um, um, okay, I need to gather my thoughts again. Um, Anyhow, I'll just go through this. Um, so you model your own plants, or you make a model in symmetry, or you get your own plant data and then make model of that, and then that model, if you have a plant data, that model becomes your surrogate model. If you have if you don't have any plant data, and then you have to make your own plant in symmetry, and then you then run it, simulate that, yeah, simulate that sensitive analysis case, and then from that simulation you make the surrogate model, because this simulation is then your own data, so this is then equivalent to your data, yeah. And then use these surrogate models for optimization. So that's basically what this is. So up until here, is there any question? Because this has to be, I mean, you have to understand this perfectly, otherwise you won't be making any progress. Any question? Okay, no, if there is none, okay. um I assume that you understand, yeah. And then once you have this, once you have your plant data, once you have your plant data, or you see a symmetry model, then you will have to look into that model and then understand and then select key parameters. So these key parameters, what I mean by that is that your independent variables, yeah, your independent variables, your x variables, your variables that you can control, yeah, basically. And then if you go to the plants, these are the things that your control valve basically are doing. Okay, so you look into this. So these are things that you can control. Okay, and then you can then make a selection. Maybe you can have like a maybe at least two. Yeah, at least make at least two independent variables that you think you can control. So select two at least. Select at least two. Select at least two, and then these two, they have to correlate, they have to correlate strongly with the independent, with the dependent variables, yeah. So y or dependent variables, these are all the same thing, or your KPI, key performance indicator, yeah, things that you want to maximize or minimize, yeah, things that like yield, things like conversion, things like uh, um, um, yeah, whatever, product flow rate or whatnot. Okay, so this could be like at least yeah, maybe, I don't know, up to you. So it's up to you. So because we will then use it later on. Yeah, so it could be like, I don't know, maybe two or three, I don't know, because you could also say, for example, yeah, at least two. So maybe one is then like a product flow rate, and then the other one is more like your energy consumption. Because for example, if you want to increase your product flow rate, you may need to purify it further, or you may need to put more energy to produce that. So at least this product flow rate and then energy becomes your at least two dependent variables. The rest you can further elaborate. Yeah. And then so this one is basically the modeling part, and then they are getting the data from the plant, because your own plant, you have lots of data, but you don't take them all, because you will be drawn in the data and then make sure that you understand what you are obtaining from the data. So this is basically this step. Yeah. And then you do sensitivity analysis. This is what I mean by simulation. So you get the data, so you then vary the x, and then record how much is then the y's, and then you get like lots of data. So if you have your own plant data, and then you don't have to do this anymore, because you're starting already from the data. Yeah, but this one is done for those who don't have any data. Once you get this, once you get the data, so here you have like a data. So once you get the data, and then you use this data to make a correlation or regressions between the x and y. So as much as possible, you try to make these correlations linear. Yeah, that means you have to then if the graph is going to be like this, for example, and you have to then try to make it as linear as possible. If not, then you can make it non-linear equations or quadratic equations. Or if you still want to make it linear equations, then you can then cut it into here. So for example, in this case, if you see this behavior, so you can just cut the operating conditions from here to there. Yeah, from here to there, in such a way that you will get only the linear part. Okay, and then once you get these linear correlations to do from x to y, and then you will then use that Excel solver to do the optimization, from which you can then get the optimum values of x, and then use that x into your simulation model. Yeah, you'll get x, which is then the above one. You get x, and then use this x to your to your symmetry again. Put it there, and then see if you have improved by then, if you have improved the y, or the dependent variables. Okay. And then if you use your own plant data, and then there's no way for you to validate it other than you go to your plant and then implement the solution yourself. But first discuss this with your engineering team, or process engineering team, or your manager. Okay. So in this one slide, is there any question? No.
Zulfan, I think you have further slides, right? Not only this one, right?
Yeah.
Plus, can you share the other slide, because last time you shared only until this slide.
Yeah, I will. Well, that's
Alright.
basically the additional slides is taken from the slide on chapter 1. So we will go through this
Oh, okay.
hydrocracking unit. Yeah. If you don't have any questions. So hydrocracking unit, I think we skipped this because we didn't have much time at the time. So I'll just go through this. Give me like another 10 to 15 minutes for this. So hydrocracking is basically, if you can see this, hydrocracking is then the one of the processes in the refinery where we crack, because we have a long chain of C. We crack it, right? And then we add hydrogen to it. We add hydrogen to this. That's why this is that hydro coming from the hydrogen, and then we crack it. Yeah, we crack it and we make the hydrogen. We add hydrogen to it. And then this is then where that unit is located is simply because somewhere here. So from the atmospheric pipe still, they call it pipe still, but there's another term for that, is then crude distillation unit, CDU, or atmospheric distillation unit, or ADU. So nonetheless, at this cut point, it goes to hydrocracker because it's quite long. If you want to make more gasoline, for example, from this longer chains, then we'll have to hydrocrack that. You can see that the resource is going to the gasoline, or in this case also some kerosene. Um, and another one is that you will have like a heavier fraction of the crude oil. For example, in this case, we have something called like light. Is that like this? Yeah. So the heavier fractions of the catalytic cracker, and then also the some of the feeds from the this residue. So this residue, it goes to here, and then some of this vacuum distillation unit, some of the vacuum gas oil, like they say, it goes back to it goes to another hydrocracker. So these are then the possible locations as well for the hydrocracker. So in this case, we aim to maximize like gasoline and kerosene. So we aim basically to maximize the valuable products. So either it's the gasoline, diesel, or in this case, kerosene or jet fuel. Yeah, whatever the lighter versions of, I mean, the lighter products that are valuable. Yeah, I think this is all self-explanatory. It's basically crack it and then add hydrogen to that. So this is add hydrogen, you add hydrogen, you add hydrogen, and then you add hydrogen. So I think last time we discussed on the mole balance of these reactions. Yeah. And then typical flow sheet is very simple. That's why I picked this, so that it's easier to understand. So typical flow sheet is very simple. So this is what they call like a one stage cracking process. Even though this says one stage, but in it there are multiple beds. Like in this case, we have one, two, three, four beds of catalysts. So we have like in this case your feed. Your feed is then here, so fresh feed. So well, typically fresh feed is then preheated somewhere, and then it's mixed with the recycled hydrogen and then make up hydrogen, and then and it goes to the first bed of the hydrocracking. So typically the first bed can be like a mild hydrocracking, or like a little bit of like a guard bed, so that it doesn't, I mean, if it has any impurities left like sulfur or nitrogen, it will be removed in here. Yeah, that's the typical situations. And then for the down of the reactors, then the cracking takes place. We have like lots of huge of recycled hydrogen coming in here to the second bed, to the third bed, and then to the fourth bed. So the more it goes down here, the more cracking process or hydrocracking process occurs. And then in the end, if this is then like a heavy oil, and then in the end over here you will have like a lighter oils, because all of these long chains, they have been cracked. Okay, and then you flash it at a high pressure vessel, and then you get the gases out, and which is mainly the hydrogen, and then they are recycled back to the reactors. You have to have lots of hydrogen. You have to have lots of hydrogen in this case, simply to facilitate. Number one is then to facilitate the hydrocracking process, because you will need lots of hydrogen. Yeah, you have seen the reactions before. Number two is that because we will need to we need to prevent or minimize coke as much as possible from the catalyst. So this hydrogen high hydrogen partial pressure will then remove or strip away any coke or minimize any coke formation. So that's the use of this hydrogen. So it's a huge compressor, hydrogen compressor somewhere here. And then we'll then have to there's a low pressure vessels somewhere here hidden. And then after that low pressure vessels, we'll then we'll then separate them into various products. So we have like a product gas. So this gas goes to flare typically, or they should be used, but then in most cases they're not used yet. And then we have light naphtha, and then it goes to the light naphtha of the for the gasoline blending. Yeah. And then also we have like heavy naphtha, the same with the same boiling point range. And we have jet fuel, kerosene, we have diesel, and then we have like heavies. So these heavies, it can go to to fuel oil and so on and so forth. And then some portion of that heavy is being recycled back to the reactor. Okay, to the reactor. So you can see here we have one control over here, right? So this is something that you can control by maintaining measuring how much is that hydrogen, how much is that the fresh feed, how much is then the recycle, and then you can then control in such a way that the concentrations of hydrogen over the hydrocarbon is maintained. And then you could also then control the this fractions over here, and then you could also then control, there's a heater somewhere here, so you could also then control the temperature inlet over here. And then obviously the flow rate, the flow rate of the fresh feed, which is then the higher the flow rate, the more the flow rate that we put into the reactor, means the lower the residence time. So residence time in this case, it's called like space velocity, as v, space velocity. So this is what they, if you have heard this term before, it's a space velocity. In our traditional chemical engineering term, we call it the residence time, but it's equivalent to this space velocity. You could also have like operating conditions somewhere. If you want to flash it at the temperature over here, it could also be like cut point is fixed, for example. But you also like a draw. You can draw it over here. You can draw it over there. You can also draw it over here. You can draw it a little bit more there. So, but be careful on the cut points. These are like typical. You could also control the pressure over here. This compressor here. It's very ugly, but okay, you get the point. So this is then for one stage hydrocracking process. There is another one which is then the two-stage hydrocracking. You can see it first here over here. So we have a fresh feed coming in. This is the same way. We have recycled gas of hydrogen. We have a makeup hydrogen. It goes to the hydrocracking reactor, and then the bottom is then sent to like a high pressure flash, and then it's a flash the same way, and then the product will then go to the distillation column, the same distillation column. But then the bottom, it doesn't go back to the first reactor, which we saw in this slide, but this bottom, it goes to the second stage of the reactor. So and then they will then do the same configurations, and then the bottom or the product will then be separate, also combined here, and then separated into one via this one distillation column. So depending on the catalyst types, depending on the severity of the operations that you want to do, and then depending on the type of feed that you want to have, and also depending on the type of product that you want to have, either one of these can be beneficial. But you have to then study this more rigorously. Hydrocracking catalyst has dual function. It has dual functions because it, like I mentioned before, it has to crack it. You have to crack it. That's number one. That's one function, and then it also has add hydrogen to that. So this is what we call like hydrogenation. So we have to crack it. That's number one. We have to crack it. And then the second function is then we have to add hydrogen to that. So two functions. So hydrocracking catalyst, because of that, it has like two functions, and these two functions, each of them is supported by one like entity, so to say. So for the cracking, we use acids. So we use acid catalyst, or acid site of the catalyst to crack it. You don't have to memorize it, but see it that you have. If you put acid to something, it will then how to call it, like a dissolve or something. It breaks. So acid is then to break it, and then to add hydrogen to that, you will need like a the metal side of the catalyst. So acid catalyst, it's things like all of this. You can see that, and then for like alumina, and then silica, and so on and so forth. And then for metals, we typically use like a platinum or palladium or cobalt or nickel catalyst. And then these are like typical catalysts. So I took this snips from the one of the three books that I mentioned before. And then this is like remember that last time we discussed on the about lumping model. So this is more like a kinetic model for hydrocracking of heavy oils. So if we have like a heavy oils, So it will then make VGO, and then from this VGO it will create distillates and then naphtha and then gases as well. And so in all of this, so this VGO can make distillates. It could also make naphtha, and it could also make gases. Yeah, so it's more complicated already, because last time we had like 3 or 4 components, I don't remember, and then now we have like 1, 2, 3, 4, 5 components, and then each of these component, they correlated to one another. So we have like until K10. So we have until K10. But then the approach to to calculate these kinetic reactions is the same. We just need to have you can use Excel for that nowadays. So we have to use like a more powerful solver, and then you have to code it somewhere. So any questions for the hydrocracking, or is there any question as well for the project? No? So if not, then okay, can you confirm that you have access to now you are looking at UTP screen? Can you confirm that? Because we will need to open Symmetry. Anybody can confirm. So Afik and Chong Yang, are you now looking at Symmetry UTP screen?
We have problem accessing because the staff account can access to the student one, but we have one student account, so either me or Chong Yang should get access.
So it means both of you don't have access yet.
We have only one student account. We got from the IT.
One student
So
account.
either just to access it, we need to use the student account. We cannot use the staff account. Right, Chong Yang?
Okay. I have no idea. But the
Are
students.
Are you connecting it?
Zes Chua, you can access the UTP account, right?
Yes, I can access.
And Daniel, can you see the UTP screen?
Hi, doctor. Yes, I can access also.
Okay. Wei Zeng?
Yep, I can access as well.
Muhammad Zulhafiz?
No, don't have access.
Huh? Say it again?
I don't have access yet.
Oh, why not?
Do you have any issue?
Do you have any issue? Hello, Zulhafiz.
Yes, doctor.
What issue is that? Anyhow, discuss with the IT Nizam. Discuss with the IT Nizam, because you will need to have access to that Symmetry. Otherwise, you won't be able to do the project. Yeah.
Later, I will talk to Chinizam.
Okay. Now, can you like Daniel E and then Wei Zheng, can you open this Symmetry? So you can just type in Symmetry, and then it's just click enter, and then you will have this window.
Yes, I can open it now.
Okay. So before we go into this, I need to show you one more thing. So you can go to help, yeah, for anything that you think you don't understand fully. You can go to help, and then you can then click on the Symmetry manual. Yeah, you can go to help and then Symmetry manual, and then this Symmetry manual will then lead you to this program files, to the installation folder basically. So you can see the program files, BMG, Symmetry, and so on and so forth. And this is then the help file. Yeah, the help file. So you can search, for example, if you want to I don't know, crude oil. and then it will then give you this. Yeah, so you can learn some practical aspects of modeling crude oil distillations, which is you can see on the left over here. So this is then in the refinery process modeling folder, and then this is then in the hydrocarbon process modeling. Yeah, you can see it over here, and then you can learn what is crude oil, and this, because this will help you a lot in this project, and also if you haven't done any refinery course before, so it will help you a lot. Or you could also say, for example, these oil source examples, and then it will give you this oil source examples. So in these oil source examples, it is under the PIONA characterization, so you could use oil source example or PIONA example. So either one. Yeah, typically people, if they don't have any PIONA characterizations, we will use then oil source. Okay, so this is where you have to then you have to go through this and then read as much as you can. So that's one. And then the other one is that we can create a new case. Yeah, if you can create a new case, I will go very quickly. So we can get a new, we click new, yeah, and then after that we will then have to take an example. So we can create new, and then once we create new, yeah, please follow me as much as you can. If I'm being too fast, let me know. And then once we create new, we will receive this. We'll see this window, configure property package or thermodynamic model. So this thermodynamic model is something that you have to select. But since we are working with the refinery, this advanced Robinson is enough. Is enough. Yeah. You can also see what this means. Advanced Robinson. You can go back to the to this one, and you can see advanced Robinson. Advanced Robinson. Yeah, you know Robinson already, but then what is this advanced Robinson? So it's under equation of state thermodynamic models. Yeah, so this advanced Robinson is then there's some tweaks in from the original Robinson model done by Symmetry. Yeah, so you can see how it is being calculated. Okay, and then for the compound, you can add, yeah, you can add, for example, you can add like, I don't know, you can add like C1, which is the methane, and then you can then press enter once, and then the methane itself, I mean the highest on the list will be highlighted, and then you can press one more time so that it is entered as one of the components over here. And you could also say, for example, C2, and then you can then use semicolon, right? And then by using the semicolon, this ethane is automatically highlighted and then all selected, and then you can add C3, and then you use semicolon, that means the C3 is selected, and you can also enter twice. Yeah, so there are many ways to enter this, just like the other software. So this is one. And then once we know this, and you could also add, like, for example, I don't know, water, for example, say something like this, and then you can then double click and double click. Yeah, I click too much. Just click once, basically. So this hypo is then if the component is not in the database, then you can then make a new hypothetical component. But at least now in this case we are using components that are available already in Symmetry. Yeah, so you can click done. Or you can then also make, okay, now I want to have like a PIONA. So you want to characterize your oil. So in this case, if you have like a crude assay already, or some assay, you can use it. So I'll show you. So just click PIONA. So why I use PIONA is simply because it characterizes it in more detail. How much is then the paraffin, iso-Paraffin, the olefin, naphthenic, and aromatics. So if we can characterize it in a more detail, then we can have like a, so to say, more accurate model. So we have so in this case we so we will say, okay, now I want to like a boiling. I want to base the component based on the boiling point ranges, and then you can name it yourself, your hydrocarbons or whatnot, and then it is defined by a boiling point. So you can also have like a carbon number, molecular mass, but boiling point is then the most available one. And then here we have like a F, so I will have to close this. I want to change the unit, so I click done, and see the unit is then filled. Now you have to change it to SI, for example, so you can have like click yes, and then you can have like an SI unit, yeah, Celsius and so on. So that window is gone, but you can always come back over here, click on the demo basis. So click on the demo, and then so PIONA. So so now the initial boiling point IBP in degree C, and then the boiling point, or the FBP, the final boiling point, is then in degree C as well. So you could say yeah, what we want to do. Now in this case, let's see. So this one. Crude. Let's say example. I don't know. If you have one, it's very easy. You know, we have it. I don't know. Just take one. Things that sound like so start fjord. So like we want to have like a heavy. I don't know. Let's see. Yeah. So this is then the atmospheric cut. So this guy is basically if you go to here, it's this one, the atmospheric cut. So somewhere here, yeah, somewhere here. So sorry, the atmospheric cut means this is in this case over here. So so we cut it in the atmospheric distillation unit. So we have lights, and then we have light naphtha or naphtha, and then we have distillate and gas oil, and then vacuum. So in this case, you will have like very light, and then this is then light naphtha, and then this all like naphtha range, and then kerosene range, and this all range. And then the gas oil range, and then your like a vacuum, your atmospheric residue range. So since we are going to use, say for example, I want just to get this guy coming. So if you follow this, and then we want to say just take one of these into the hydrocracker. So we will say that, okay, now I want to have this into my hydrocracker. Yeah, the yield is like in this case 76%. Yeah, the yield of this crude. So this crude Peregrino, the heavy yield is 76%, right? So it's quite a lot. It's quite a lot. It's very it's a lot. And then you can have you have like a viscosity curve. We have like some total sulfur, mercaptan, and so on and so forth. And we have the API gravity, and then we have the asphaltene. Now I want to see the, where is my yeah, I want to see the boiling point. Is that not here? Yield graph. No. No, this is not not a good example. This one is because this is open source, right? You can use it for your study. So you have a lot. I don't know. Tapis maybe. Yeah, let's see Tapis. So this Tapis. So this is then the vacuum gasol that we want to use. We want to crack this further. So you want to crack this. So in this case, you can then see, because this Tapis is quite light, and then the you can see the vacuum ratio is only like 5%, and then this vacuum gas is only like a 23% volume. and then we have so we need to have this, and then the other sulfur, and so on and so forth. We have the viscosity, and then we have the and then we have the so we have to make it yellow. So we have the boiling point, but this is in Fahrenheit, so we have to convert it into to Celsius. Minus 32 divided by 9 times 5. So we have them in Celsius, so you can easily then put it to this guy. So now the initial boiling point, once we have that, yeah, so we want to correct this basically, yeah, we have to correct it. So initial boiling point is this one, so like 344, just like put, so that means this is then 344, and then the heavy sorry, the final boiling point is about 535 or something. 535, and then it gives you like an so this warning is like giving you the idea on what to do, and then what still needs to be done. So in this case it says like well, you have specified the boiling point range, and then the names you could yeah, it's based on the boiling point range. Use a prefix and then suffix is in Celsius, so that you can know. And then in this case, we include the paraffins, iso-Paraffin, olefin, naphthenic aromatics, and then dehydrogenated aromatics. So dehydrogenated aromatics is what we call like a polyaromatics. Okay, and then atomic inclusion. In this case, you can add it or you don't. And then in this case, we have something like we have something like this. So we can have sulfur and nitrogen. Sulfur. We can have sulfur. So this sulfur and then nitrogen, right? So you can add these two as well, so you can include that. So this is aromatic, so we don't include it, we don't have any data on that. And then yeah, just leave everything to default and then create slates. So once you create slates, it will then give you a long list of components like this. See, so this long list components. So remember that you notice that we only added like this 4, but then we have like a long list of components. Paraffin from like 344 to 40 something, and then goes to like 500 degrees C, and then the same goes with iso-Paraffin, olefins, Naphthenic, and then aromatic, and then the dehydrated aromatics. Yeah, so it's more like your slate, and then we can say done. You can say done. So if you take because this is like a oil, right? So this oil, we have to get then from this oil data regression. So now before we go to that, because Symmetry is using Microsoft Visio as the interface, so you will see Visio like theme. So on the left hand side here, you can see all kinds of options. In this case, you can then click, and then you can see main shapes. So these are the shapes: material stream, signal stream, energy stream, and then all the typical unit operations, which we can then drag and drop. And you have also like a closed plant unit operation heat exchanger. You have a heater, cooler, heat exchanger. You have a fire heat equipment, fire heater, burner, boiler, and then oil data regressions. This is what we have to use now to make that oil, because we have only like the compositions. So you can see if I drag and drop, drag, and then you can zoom in, double click on that. You can say, for example, I'll spend some time here just quickly. Say for example, I don't know, you can have a feed and then name it, and then here we have like we have to specify temperature, pressure, and then the flow rate, and then we also have to specify the component fractions. But since we don't know how much paraffin at this boiling point, how much paraffin at that boiling point, how much iso-Paraffin, olefin, and so on and so forth. So we need the help of that oil regression, which we are going to do, which I'm going to show you. Now just simply for complete to make this complete, we have all kinds of property calculations. We have all kinds of reactors, all kinds of reactors. All kinds of unit operations are here. Just a matter of like a drag and drop. So you need to know which unit operation you need to simulate to model and then simulate later on. Okay, now as I said, we need to give the composition. So this composition is coming from the is predicted. The composition is predicted from this assay data. Yeah, I'll show you. So we go to the oil source, and then this oil source is then double click on that. Just double click. Okay. So now you see this. So you can anchor this. Yeah. So keep window on top. Keep window on top. Anchor that one, and then you can say, well, I don't know, maybe this is then tapis. So this is the new tapis, oil source tapis, and then it is connected to the to this feed. Yeah. So either you can then click this drop down, feed in. This case in means if you go here, in means this one is in at the beginning, and then out is over here. So and then the calculation will be somewhere in between. So it will then take information from the inside, and then it will then calculate what the outside should be. So that's how the solver in the symmetry works. We can either use that drop down menu, or we can just drag this and then connect it to the see glue. So connect it to here. So it's just like a VCU. Yeah. So okay. So now you can see it is connected to the feed already. Okay. So now what we have, because this is like a heavy gas oil, so there is no light end, but we do have like a distillation curve, right? So in this laboratory analysis, we have to fulfill we have to add distillation curve, and then we don't have any density curve. We don't have any atomic inclusion. Yeah, we could. Let's see. So if we tick on this, sorry, if I tick on this, tick distillation curve, you can see all of these steps. Yeah, summary, setting, equilibrium, and so on and so forth. So if I tick this, and then that means we are going to key in what the distillation curve looks like. So we go to this tab, and then we do it one by one. Yeah? We go to this tab. Yeah, it takes some time somehow. And then I will then yeah, so that we know what we are doing. This one, and this is from 0 to 5. How many? 13. 1, 2, 3, 4, 13. Let's make it 13. So so we have like 0 or the initial boiling point. So 0, 5, and then 10, 15. No, 10, 20, and so on, so on until 95. Okay, 10, 20, 30, 40, 50, 60, 70, 80, 90, 95, 100. So that's all. And then you can also copy paste this. Yeah? Copy, and then you can paste this as a specified. So you can paste this. So once you copy paste, and it gives you this so it's already calculated automatically. Yeah, so automatically calculated, and then it gives you like a regress line, okay. So for the boiling point, make sure that this is then the TBP. So you have the TBP through boiling point. So this is the TBP through boiling point, because there are a number of types of distillation curve. Yeah, make sure of that. And then the basis is then volume. So this is the volume. See, volume. Yeah. What else? Yeah. So we have key in the distillation curve, and then we could also key in, for example, in this case, because we have I see that we have viscosity. See, we have viscosity somewhere here. So you can add that viscosity over here. Right. So somewhere here, viscosity. No. So we can add so centistoke is kinematic viscosity. So you can click tick on it, and then this kinematic viscosity is there. And then the unit is so there are how many data? Three data, so you can add 3. So the unit is meter square per second. Meter square per second. So you can Google yeah, because Stokes Stokes. If you don't know, yeah, if you know, then let me know. Stokes to this one. So 1, 2, 3, 4, 5, 6. So 1 divided by million. 1 divided by million. So in this case, you could then say, okay, so 1 divided by million. Where is that guy? So 1 minute. So 20, 40, 50. So 20, 40, 50. And then what we specify is over here. So this one divided by 1 million. Okay, I don't know how much that is. Divided by 1 million. Sorry. Yeah. So this one is then how many 0? 4 0 0.1234 3952 1234 1774 1234 1231. So you could do this. Okay, and then it predicts to you. It predicts for you like okay, so it's not really nice prediction, but okay, I mean it doesn't follow this one exactly, but it's something that you can then play around with this number. But in this case, in this example, it doesn't matter, yeah, because we are limited by time. So you could do a lot more, and then you could also say what else data do you have? Just a few more, and then you can see. So we have API. We have hydrogen. See, we have this hydrogen to carbon ratio, which is this one, hydrogen to carbon ratio. Hydrogen is below. So this one is then so this is then hydrogen divided by carbon ratio, so 0.2. So by mass, yeah, and then this is also by mass. So you could put it there, and then you put like 2 by mass, and then the density. I think you have density. See, density, which is 864. 864. Okay, so now in this case, and then it says ready to regress parameter. So we simply regress that parameter, I guess, parameters, and then it will then try to calculate this as much as possible to be as close as possible to the specified one, and this one as well. So so apparently the hydrogen to carbon ratio is not they don't match, but you can play around with the scale, yeah, with the scale, and then this one's also so it gives more weight to the density, and then rather than the hydrocarbon to hydrogen to carbon ratio. So if you put like a bigger scale, I don't know, let's see what happens. It doesn't match. No, it doesn't improve. So nonetheless, okay, so let's keep it this way. You could play around later on. So it says that it's regressed, but then the material port is not solved. So that means this port is not solved because this stream is connected to this stream, yeah, feed. It's not solved because we are missing the information. So we either put the information in here, or we put the information on this. So in this case, you can see, because we have regressed that, and then you can see all the components are already here. See, the components are already predicted by that regression model. So it doesn't predict for us, says there is no dehydrogenated arom. You can have only like aromatic, naphthenate, olefin, iso-Paraffin, and paraffin. Okay. Then the operating condition, for example, this is, I don't know, 30 degrees C, and then maybe 2 bars or 1 bar, I don't know, 1 atmospheric. So it is 1 atmospheric, while the unit is then kilopascal. So you can type 1 and then press space. Yeah, type 1 press space, and then the default unit, you can then select the unit, yeah, and then atmospheric, for example, in this case. And then you want to say, okay, so it's like coming from the tank, 30 degrees C, atmospheric, and then maybe, I don't know, maybe 20,000 barrels a day, for example, and then you can put it over here. So 20,000, because it's a standard liquid, yeah. So 20,000, and then because the unit is then meter cubic per hour, so if you say 20,000 barrels per day, so we can then press space again. Press space, and then barrels per day. I said barrels per day. Barrels per day. So 20,000 barrels per day is about 133 meter cubic, and then it's equivalent to about 100,000 tons an hour. 100,000, sorry, 110, 114, 15 tons an hour. Okay, 115 tons an hour. That's basically what it is. And then you can also see in this window, you can see equilibrium results, the bulk, and then if there is any vapor in it, you can see. So this stream, just a refreshment, yeah? You have like a vapor fraction is equal to 0. That means it's all like liquid form, and then there is no vapor, so that means there is no vapor fractions, all liquid form. And then this liquid one is this, if you have like a water or something. And then you can have like the properties. So you have properties like the enthalpy, entropy. These are all like not really useful. You need to have like the delta for that to make it useful. But you have like a predicted molecular mass, and then the density, which is the predicted one, the 864, and then the predicted heat capacity, and so on and so forth. Yeah, the Z factor as well. And then you can also see like more properties. You want to see more properties. For example, in this case, we want to see like hydrocarbon properties, because this is hydrocarbon. So click on this, and then you can go here. So this one is more to give you like a more detail on the predicted properties, molecular mass, specific gravity, API gravity 31. Let's see how much API gravity does it give you. Oh, this one. Yeah, so it's the data says 32, and then it is predicted to be 31. So which is this two is not that bad. Viscosity and so on and so forth. Yeah, so fuel properties as well. It predicts you the Ron number, volatility, the rate vapor pressure is not there, and then the combustion properties and so on and so forth. So you can go through this and see the data. Yeah, and then also predicts this despite PIONA analysis. So that's the good thing about that. So it predicts for us that, okay, so this particular crude, it has this 27% of paraffin to the 23% iso-Paraffin, olefin almost 0, Naphthenic is 32, Aromatics 16. So if we just make a quick comparison, do we have something? I doubt that there is something like this PIONA. Oh, we have this PNA, Aromatics. So the paraffin, it doesn't mention about whether it is iso or paraffin. So it says 49, close to 50. So if you add this 27, 23, it's also like close to 50. So paraffin, in terms of paraffins, it can predict it quite well. And then Naphthenic is 32 predicted. This one is also 32, which is also not bad, right? And then the aromatic is predicted to be like 16, while the data says it's 18, which is not bad at all. So so it's very good. So that's why I like this PIONA stuff. And then Sarah is more like a cytomatic, aromatic hexanosulfate, which we don't have the data to compare. Elemental analysis is also like something like this. So you could do so. But this one is a bit off. Yeah, this one is a bit off. Any case. So we have that one. So here, for example, we can then pump it. Yeah, just to show you quickly how to use this. So you pump it. Before we go to pumping. So if I double click this, and you see all of these are like highlighted, and then this means that they are calculated values, and the rest also calculated values. But the bold numbers, this dark bold, black bold, these are inputs. Is our input. Um, so these are the things that you can then specify. Okay, so that's your what we call degree of freedom. And then we connect this to this pump, and then this pump is then the, so we have to specify something for that pump to be able to calculate, right? So this feed is connected, and then the outlet stream is not connected, but you could also say, okay, now I just type it here. If not type it feed, can you know? No, we cannot do so. I thought we could, but nonetheless. So connect it over there, and you can see it's not being calculated. It's a dotted line. So it says missing delta P. So this delta P is then the, yeah, you know that how pump works, right? So if you know how pump works, you need to know give that the head. So in this case delta P. So you could put delta P or pressure ratio, or you could put like the outlet pressure. So in this case, for example, if you know that hydrocracking works at about I don't know, about 70, 80 bars to 100 bars or something. So you could say, okay, now I want to pump it to 100 bars or 80 bars. So 80 and then space and then bar. Yeah. So 80 bars. So we pump it to 80 bars. But this one, it says, well, we are still missing one. So this is the efficiency. So that efficiency from the power to the pump. Yeah, from the motor to the pump. So this efficiency we typically use like, I don't know, 70% or something. And then we have the outlet stream is being calculated already. Okay, so and then you can then so say, okay, now I want to add heater. So I want to increase the temperature a lot more. Before I go there, you can see that pump has two degree of freedoms. So the efficiency and then the outlet pressure, or the delta P, or pressure ratio. So you just out of this delta P, pressure ratio and pressure out, you have to specify only one, and then the efficiency is then for the thermal for the energy balance part. Again, for the heater, say for example, yeah, delta P, it says not solved, but you have to put the degree of freedom. So for your heater to work, you need to know how much is then the heat that I have to add, right? So it is then how do you call it? It's given by the delta temperature, or it's given by the outlet temperature, or the inlet energy that you put into that heater. So typically we will then use the outlet temperature, because we know that we are controlling the outlet temperature. So we can either put it here or there. Yeah, either here or there, because this is an in, this is an out. So in this case, if you say, okay, now 400 degrees C it is, so I put it over here, and then automatically it's over there, or you can just put it here. Yeah, up to you. And then the delta P, well, 0.3 bar should be enough, and then it is solved. It is solved. So you have already the outlet stream calculated, and then you can add material streams, something like that, and then you can have it there. Okay. Now, and then from here you can also, because it's from the slide. So basically we have like a fresh feed, which we have already identified, and then we need to have like a hydrogen coming in, right? So we need to have hydrogen coming in. So in this case, we can then add hydrogen. So add another hydrogen stream. So so hydrogen. So temperature in this case, well, let's for simplicity's sake, so let's say that it is already like 400 degrees C. And pressure is also like 80 bar, right? 80 bar. And then how much is this? Yeah, this is something that you have to calculate yourself, and then make sure that it is enough. So we have the feed to be like I don't know, 306, 300, and then the liquid volume is 133. So if you go to literature, you will then find out how much is then the typical ratio of hydrogen to the hydrocarbon. But as a startup, you can then say, okay, I want to like I don't know, make it double or triple. So let's say if you want about 300, right, and kilomole. So if you triple it to be like 900. Sorry. This is good. So this one is like a 900. And then it's only hydrogen. You don't have any hydrogen, so you can see. Now in this case, you can then close this and then go back to the demo. Then you can say, okay, I'm missing hydrogen. I can add hydrogen. So hydrogen is down the line here, new. Okay, so now you can add hydrogen. Where's it hydrogen? Again, see. So pure hydrogen, assuming pure hydrogen. So 1 and then enter, and then you will have like another window coming in to make it more detailed. So it's small compositions or mass, it up to you. It's the same. And then click OK, and you will have like everything's calculated, which is then pure hydrogen. Okay. So you have hydrogen, and then you could also then you either mix it, or we can directly go to the reactor. For example, in this case, hydrocracking. Hydrocracking. No, this one, hydrocracking. This one, yeah, hydrocracking. So we can then double click that. Add required components for reaction model selected, continue, yes, and then you will see it adds automatically the necessary typical components necessary for this reactor to function, which is down below. So it adds isobutene, propadiene, carbon, and so on and so forth, yeah, until ammonia. Okay, so what is not added previously, it has been added now. Double click on that, and then we'll see yeah, this window. So this window, we have like a feed, right? So we have feed in, which is S2. S2 is then our feed. So S2, and we have hydrogen in, which is then hydrogen out. So hydrogen. And then we are not using any catalyst movement, so we just product out is then something that we can type. Okay. So you have feeds coming in, hydrogen, and then product out. So it says it's missing bed number 1 height. So we can see reaction mode is then heavy gas oil, because it's heavy gas oil basically. So reaction phase is liquid. We specify bed temperature also by default here. So bed type is then fixed bed, and then surface time, well, you can add it, you can not add it. It's more on deactivations and stuff. So number of beds, if we say like 1 bed or 2 beds or 3 beds, it's up to you. So you can put like, for example, I don't know, 2 beds. And then if you put 2 beds, and then you will see 2 beds over here. Okay. And then you have to specify the bed height. So in this case, I don't know, maybe like say 5 meters. It's also like 5 meters. Second bed diameter, I don't know, 2 meters. And then 2.1, right? 2.1 to 2.1, and then the fully distributed. And then this catalyst functionality. So its function, if you're in a drop down menu, you can see there are a lot of functions over here. This one you can see from the help file, hydrocracking. I think somewhere. This one. So you can read through this. Yeah, you can read through this. Guts, cracking, hydrogenation, and then main is then all of these mixed together, I guess. Main for middle stages. Yeah. up to here. And then we have done this summary. So this is the catalyst detail. So diameter, for example, I don't know, maybe 1 inch. I don't know, 1 inch, 2.5 centimeters, or maybe one centimeters. And the aspect ratio is about the whether it's sphere or not sphere. So you can go through here, sphere or not sphere. So if it's not so sphere, so we can add I don't know, maybe 2 or 3 maybe. And then the catalyst density is over here, maybe I don't know, 1500 kilogram. And then missing sintering temperature, so it's at the temperature at which the catalyst starts to sinter, maybe 400 degrees. Preheat temperature, so recycle preheat temperature. So if we want to say, well, it goes in 400 degrees C, and then preheat temperature is about, yeah, also like a 400 something, 400 I don't know, 400 degrees C. Says no hydrocarbon nitrogen content because we haven't specified any nitrogen in the stream, so we can go to atomic inclusions. We don't have any sulfur and nitrogen in this example, so remove this and then remove that, and then it's time to solve, but you have to we could also, there's also an option here to make it quick. Or speed up. We could also speed up. So it's just like a matter of different types, different mode of calculations. We have to wait. And if you have any data from your plants, and then you can then fine tune the kinetic parameters in this default. In the default, so you have all of these kinetic parameters, so you can increase or decrease one item from to the others, so that you can then try to match the data with the calculated results. Yeah, see, you can also say speed up. So if you speed this up, it will then hopefully it will be quicker. So it was like 400 iterations, now it's only like 62 iterations. So but you have to be careful. So now what I want to show you before we go to the actual case, I want to show you two things. Number one is that we know, so we have hydrogen coming in, and then we can also separate this hydrogen nitrogen, because this is all huge of hydrogen. It's a huge of hydrogen in it. So you can see this outlet stream, it contains lots of hydrogen. See, lots of hydrogen, 74% hydrogen. So we have to remove it. We have to cool it down, for example. Now, to cool it down, and then outlet is about, I don't know, maybe 50, 60. And then we remove the it automatically removes it because it's a high pressure, so we just simply cool it down and then remove the vapor. So this vapor stream, it contains lots of gases. See, hydrogen, almost pure hydrogen. So so this is then the hydrogen, and then this is then the liquid sample. Okay, so so we need to compare. The what is then the difference between this and that. So we expect, because this is then the heavy hydrocarbon. This once we crack it, yeah, with two beds, we hope that this will be going to be like a lighter versions of this hydrocarbon. So we can see from the distillation curve. So you can see distillation curve. And then we have to connect this stream to that distillation curve so that it gets the data. So one way to do that is, oh wait, yeah, takes some time. Oh, I haven't saved this. Let's see. Oh, I haven't saved this. Remember to always save your case, yeah. Remember to always save your case. Okay. Anyhow. Be patient. I know that I'm going very quick. I'm going very quick, but then the idea that I want to convey with you that with this you can build the simulation model for your plant, and then that's how you do it. So if you play again the recording and it's more slower pace, and then hopefully you can follow. I want to introduce you as well to the concept of this degree of freedom, as well as because this degree of freedom is basically related to your independent variables on the stream, on the plant. Yeah, your independent variables. So you can see that this pump. So you want to increase the power. If you increase the power of the pump, it means you will then increase the pressure outlet. And then if you remove energy from this cooler, that means you will then reduce the temperature there. So the way you remove the energy, obviously in this case, you will then increase the cooling water flow rates on the air cooler, and so on and so forth. Yeah. In this case, for heater, you will then add more fuel. So this adding fuel is like independent variables. So and then this temperature. So temperature here is then the control variable. So if you can see from this flow sheet, yeah, you can see it now. It's thinking. Anyhow, I don't know what is happening. Yeah. Okay. So up until here, so this is how you yourself make a simulation model. You can play around with this, get your own plant, and then model it yourself while you have the license to do so during this course, right? What I want you to do as well. So you can now, number one, get your plants and then you model it the way that I'm now modeling this. That's the one way. Or number two is that you get your plant data, like I mentioned to you, and then number three, and then use that plant data to make the regressions. And then number three is the what I'm going to show you. So we will use the yeah, because some of you may be well versed already with this hydrocracking, some of you maybe not. So I'll show you where to get the examples of this. I've opened it somewhere, but okay. So I'm going to show you where to find it. Yeah. So you can go in this in the installation folder basically. So I opened this already. So you can go, you can click open, and then in this case it goes directly, not goes directly. It can go to this. If you don't know, in the symmetry and then documentation, you can either click on manual examples or plan examples and so on and so forth. So this particular model is in the manual example, and then you go to reactors, and then you can go to in this case hydrocracking, yeah, which I opened it already. So this hydrocracking, we have very limited time. So you know how to do this already, and then it gives you like switch shape to like a 3D, yeah. Also this 3D or 2D. This then the 3D. What we're doing is like a 2D visual, but it doesn't matter. And we have this hydrocracking reactor in front, and it has this hydrocracking reactor. So the hydrocracking reactor, okay. So you saw this already, the hydrocracking reactor. So it has like 4 beds. So it has 4 beds, recycle rate of 400 degrees C, and then you have like yeah, these all different 4 different beds, cracking 2, cracking 1, cracking 1, and then main, the catalyst details, and then the yeah, and all of this. So it is more complete because it's example. So it includes nitrogen and sulfur, and then you can have the profiles of the unit here. And the length it goes down here. So 20 meters in length, and you can see the temperature. You can see the vapor fractions, and then catalyst temperature, pressure, conversions, and so on and so forth. You can see the conversions increases until 37%. So catalyst activity. So you can see the profile of the whole batch in this hydrogen, coke, and so on and so forth. You can go through this. So what I want you to do is to understand this flow sheet. So I'll quickly leave you. We'll go through this very quickly. So we have the hydrocarbon mixed with the recycled hydrogen, and then this is what they call like a hot recycled hydrogen. So it increases temperature from you can see. So from this G1 from 64 degrees C to 200 degrees C. Yeah, it's specified the temperature over here 200 degrees. So this is then one of your independent variable. So you can increase this temperature or you can reduce the temperature and see what happens. Okay, so that's one. And then you can also and then this is then this mix of fresh feed. It goes to this hydrotreating to remove the impurities like nitrogen, sulfur, and so on and so forth. And then it's treated heavy GO already, and it is mixed with with this guy. So the bottom of the distillation column, and then this is then if you can see in this splitter. So they specify the split in the splitter. The UCO recycled is in here, and then it is specified to be 35,000 kilograms an hour or 35 tons. Yeah. So the total volume, if the bottom BTM is 55 tons, and then the 35 tons is being recycled and mixed with the feed. Okay. So to make more to produce more products, and it goes. So you can also control this. Yeah. So in the plant you will see this like a valve that you can open. So if you open the valve to the recycle, that means you will then increase this flow rate. If you close the valve, and then you will then reduce the flow rate over here. So this is another independent variable that you can play around and see what happens. And then this pipe is let's see. Pipe is in this case just to I don't know, just to simulate some heat loss, maybe from 431 to 400 degrees C. So you could also say, okay, now I want to increase this to 410, and then reduce it and see what happens. So this is another degree of freedom that you can use. And then they mix, and then it goes to the hydrocracking reactor. And then this hydrocracking reactor, I think I mentioned this, right? So you can play around with the temperature, and then this hydrocracking temperature. There is another recycled gas going into here. So the recycled gas is there are. So this recycled gas is split into three, 1, 2, 3. So out 0, out 1, and out 2, and then they specify the out 1 and out 2, which is then RG1 and RGQ. So RG1 is basically the one that goes to to mix the hot recycled gas, and then RGQ is then the cold recycled gas. So in this case, you can play around if you want to put more cold recycled gas or more hot recycled gas, and then you can then see what happens. Yeah, see what happens. What else? Yeah, acid gas is simply like because once we treat, you have this how do you call it, the sulfur and acid, the C and or whatnot. It will then be split here. So you will see here The out one is then the acid gas over here, and then LP recovery or recycle is then your light gas recovered, which should be mainly hydrogen. So in this case, you can see the acid gas contains like hydrogen 40% more, but then the light gas recycle is 91% hydrogen, which what we expect. And then see the hydrogen sulfide is then all the hydrogen sulfide goes to the acid gas. So this is like a simple acid gas treatment. So you can just split it because this is not our concern now. You could model it though using your own plant configuration, but in this case it's easy. It's easier to do it this way. And then this is then high pressure separator, and then this is then what we call low pressure separator. So you can see the pressure is then reduced from 170 bar to 20 bar, yeah, from 170 bar to 20 bar, and then the temperature is increased a little bit, so by somehow. So you can play around. So these two are like your independent variables as well, things that you can control. For the high pressure vessels as well, you can also see the same configurations. So they specify the pressure. So it just drops by 81 kilopascal, or less than a bar. But then the temperature drops from 400 degrees C to 35 degrees C. Yeah, from 400 degrees C to 35 degrees C. So 400 degrees C is then this effluent tap stream. This effluent stream is 400 degrees C, and it mixes with wash water, which is this 25 degrees C, and then you get what you want. And then in this distillation column, it's a lot to digest, I know, but it's something that you can see. But you see this in your plant anyhow. So it's operated at 4 bars, yeah. And then you can play around, like reduce it to by 3.9 or increase it by another 0.1 bar, and so on and so forth. So you can see all of these are like you control the temperature in the condenser, 60 degrees C, and then the reflux is 30, and then the light naphtha draw. So you can draw light naphtha over here. It's 1000, and then heavy naphtha 7000. You draw it, and then the what else? See, also you draw like a light distillate to feed ratio 0.08, and so on and so forth, 0.27 for heavy distillate, and then this is then the bottom flow rate to 55,000. And then you can see the product, or in this case the product that they really want is then somehow this one, the kerosene, and then the light distillate. Okay, so they are being calculated. The rest are being like somehow controlled in one way or the other. Is this not? No, it's not working. So in any case, what I want to see, what I want you to do is that there are many the bolt. Remember that black bolt is things that your independent variables. Yeah, these are all your independent variables, and then these things are your dependent variables. Okay, the ones that is not bold. So you can then play around with this dark bold, so that you can see what the effect that it has for the dependent variables, and then just pick one or two, at least two, right? At least two, and then see what happens. Before you go there, I want you to let me see. So just to show you because it shows this curve, right? Just to give you an idea. So this curve, yeah. So this is what I want you to see. You can see this light naphtha, right? It starts at about this minus degrees C. It goes at about 140 degrees C, 120, 140 somewhere. So it's very light. And then if you compare this heavy naphtha, so this is also the same thing that you will see in the cut. So you can see this is then from, yeah, I don't know, 70, 80 until 200 degrees C. Yeah. So this one is heavier, obviously, from this guy. So this is something that you can compare as well. And then if you see the code over here, so you can what is that stuff? Property calculation and distillation curve. And then you need to make another, because this line has to be connected to there, yeah, like this one is connected to there to get data. So we can double click on it and then create another port, because the original port is connected to this mixer. See, the original port is connected to this mixer, so we need to create another port. Oh, it's already there. So sorry. So I don't need to do this. So this fit, curve fit. It's already connected, so you can the way that you can do it is then by create port, click here, and it will get another out -1 port. So this one, so it is here. You can see the fit is very heavy. See, it's from 300 until 550 something, and then this, it says this product. I'm not really sure. Let's see, product, because I'm supposing this one, because this is then the outlet of this. Yeah, after all the gases are removed, this is the one that we are going to get and then to separate. So looks something like this. So they must have taken the no. So what it does is this product is just a mixture of this LN and then out _1. So if you see that this one maybe is they create another port from this guy. Say they create another port from this guy. One is then going to so the original port is then going to curve _LN, which is this one, and then the other port is then goes to M port, this one. Okay. So so basically what they do is that they mix all of this graph, they mix all of this stream and then as a product, and then calculate what the boiling point curve is. So you can see, so we have like half an hour to go. You can see give you an idea. So you can see now, can you see this is your feed, this is then your product. I don't know. So while it is very steep from 300 to 500 degrees C, and now we have like some portion of it is like a very light, so we should see very light, and then the majority, like from this, I don't know, it's maybe 1 or 2% over here, up until 400, maybe somewhere here. So 1 or 2% until 90% is then from 100 degrees C until 400 degrees C. See, about 90%. About 90% is 400 degrees C and below, while in this case 90% is then 500 something, and then it's a lot. So this one is then the feed heavier, and then this one is then the cracked hydrocarbon, the cracked feed, so to say. So we can see that the majority are already in this nice boiling point range, the products that you want, which is then the naphtha up until 200 degrees C, somewhere here. So it's about 30% of this product is then the naphtha, and then from this 30 until say for this 400, so about 30%. Sorry, 20%. So 20%, 20% is then the naphtha, and then the 70% is then your diesel, kerosene, and then jet fuel range, which is a valuable product. While in this case, your diesel, there's no naphtha, and then your diesel is only like 15%, roughly 15-20% is then your diesel. While in this case, your diesel is 70%, and then naphtha is 20%. So it is then the use of this hydrocracker unit. So what you can do, you use sensitivity analysis. So for example, in this case, you go to tools and then case study, make a case study. You select the independent variables and then vary that. So case study, and then in this case you make it on top always, and then say for example you want to oh, in this case I forgot to mention to you, specify this hydrogen to hydrocarbon ratio. So it specifies this hydrogen to hydrocarbon ratio to be like 1200 cubic per cubic, which is a lot, yeah. And then it gets this feed from hydrocarbon, so it's the same. Yeah, I showed you earlier that this is then a right click connection. I don't know. So let's see. So this 147.9 is this guy basically. Sorry, so I put it here. See, 147.9 is that guy. So if I put it over here, so if I copy, you can copy here, yeah? And if I copy it over here, just to give you an example, so copy connection, see, not copy or copy whole table, but copy, not copy path, but copy connections, and you put it over here, so anywhere, and then you paste connections, and you'll get this number copied. Yeah, that's how you copy. Yeah, copy connection and then paste connection. That's how you copy things. And then this the recycle. This is then the recycle, which is this guy. This is the recycle. So it's supposed to be 39. See, 39.48. So this guy is then copied to here, which is done already. So so we have like two hydrocarbons coming in, right? So this guy, the fresh feed, and then the this hydrocarbon, the recycled one. So just sum them. We just sum them, and then you will then get how much is then the hydrogen, because this one hydrogen. So you sum them, and then you multiply with this ratio, the one that you need, and then you will then get this meter cubic per hour, and then you then calculate what the mole is for the hydrogen, and then the this actual hydrogen is then the recycled. You can see if you click on this, you can see it's import from high pressure HP underscore rec, HP underscore rec, in this case, which is this one, HP underscore rec. So this is then the number, the 7 what is that more, HP underscore rec, moles. Yeah, it's supposed to be, I don't know why this is different. 1 minute, yeah. Mole flows in hydrogen. Oh, hydrogen only. Sorry, this is hydrogen only. You can see. Can I see? See. Mole flows hydrogen only. So you can see the hydrogen only is 7966. So this one 7966. So you need to know. You need to have like a hydrogen. This is then the actual hydrogen that is being recycled. And then since we this is then short of the 1200, so we have to make up. We have to use makeup. So we will then calculate the makeup flow rate. So it has these makeup fractions which you can then calculate, which you can then specify. It's also specified. The 96% is specified. And then the flow rate is then calculated accordingly. The missing flow rate, which is this. So this one is then sent to this guy, the 21 something. So this one. So 2150, which is this one. Yeah. So it is coming from PC underscore H2 ratio. So PC underscore H2 ratio, and then sheet 1, which is sheet 1, and then B11, which is B11. So this one. Okay. So that's how it is done. So say for example, you want to vary this. So we have only like 20 minutes. So I took this as one of the dependent variables, yeah, as an example. And then we will then vary this as an independent variable. I can then right click and then add to case study. Yeah, But this window, this case study window, has to be opened. Otherwise, this option is not available. I'll show you. So if this is not if there is no case study window, I cannot then add this to case study. There's nothing. So yeah. So I repeat, yeah, this case study has to be there so that you can then add the dependent variable or independent variable to the case study. So in this case, you can then right click and then add to case study, and then this obviously as independent variable because this is something that you control. You control. So independent variable, click OK, and then by default it goes to like a stepwise of 11, and then you can say, well, it's 1200. Say, can I then see if I increase it, if I change it? Yeah, because you want to see what happens to the plant. 1100 for example, I don't know, and then 1300. So you only vary that by as maximum like plus and minus 10%. In this case, so 10% is about 100. So 1200 plus and minus 100 is this number. So you can have like 11 points. So maybe for the sake of simplicity, just make it 5. And then so this is what you vary. This is what you vary, and then you want to see how much is then keeping the other constant. Keeping the other constants, you want to say how much is then your what was the product again? Say you want to say, okay, how much is then my kerosene, for example. Just right click and then add to case study. Obviously this is then the dependent variable, and then this one as well, like distillate, add to case study. And then maybe you want to see, yeah, I want to see how much is the energy required, right? So add to case study as well. So as three dependent variables, and then you can before you can then run this is run local or run local parallel. So I suggest you to run in parallel so that you can use multiple cores, more than one cores. So you either click this drop down menu or go to setting and then use this one. See, yeah, parallel. See, this parallel. Okay, and then you can click run, and then you will then run these 5 variations, and then you will see what the effect it has on these 3 dependent variables, the kerosene, light distillate, and then the reboiler. Do you have any questions so far? Yeah, I know that I'm very fast because simply we don't have much time. Yeah. But we go through this recording again. Hopefully you can see it much clearer. You can see it, yeah, if you status. So it's now solving case study 1, which is then this case study 1, and then I don't know which one. So it's not completed yet. So it will take a lot of time. So I suggest that you start thinking and then start familiarizing yourself to this. And then you may need, or for sure you will need to run this overnight or in a couple of days to get sufficient data for you to work. Yeah. Or if you have already like your plant data, that's easier. Then you can skip all of these steps. Yeah, get your plant data and then make a regression model out of that. But in this case, since you don't have the plant data and you rely on this simulation model, so we'll assume that this simulation model as your plant, so to say, and then you let it run overnight or a few days, or maybe over the weekend, and see what happens. Any question? Yeah.
Dr. Sufan,
Yeah.
I have a suggestion. because all of us are using this one on the UTP computer, right?
Mhm.
So I don't know if we can leave it like running for a longer time because other student might interrupt the simulations. So my suggestion is it possible that this one are you running on your own PC or also in UTP PC?
This is my own PC because we are supported by Snumbo J, so they gave me this license for 2 months only. And then
Because
since you guys
in
are
the
from
end,
UTP, so you should be able to
yeah.
access this. So what we typically do is that we in your case, because the students are far away, so they can ask Jainism to put like this like a note, do not disturb. So that's what we typically do. So do not disturb. That means that
see.
computer is not cannot be used by any other students. Or you can run it like over the weekend. So hopefully it's less disturbance for you. Right? So at least
Because
like 2 months.
in the end, we're going to use this data for the programming, right? The optimization, the linear
Yeah.
programming, so to speak.
Yeah.
Is it possible that maybe for those who do not have their own data, we provide them with this data from the Symmetry, the results, or this is part of the project to get the data?
Yeah, because this data will be unique for everybody,
Oh,
right? This data is about dependent and independent variables. So everybody should pick an independent variable and one independent variable is different from the others, right? Well, if any of you like Afik or Chong Yang, you want to run this for them, it's also fine with me. And then you can pick as many the many independent variables and then many dependent variables. So once you get this run and then you have the data and then you can give it to them. That's also I think a way.
or if you don't mind, we can use this data that you are generating now.
No, this is just an
Is it
example. I'm not
Oh,
generating any data. This is just an example. So it's only like 5 data points.
Okay, so they
You
get
can
more
you can
data
you can
points.
you can repeat what I do with more data points, like maybe I don't know, maybe 10 example, or maybe 5. But this is only like 1. Yeah, it's only 1.
Okay.
It's only 1 independent variables, and then 3 dependent variables that I put. Yeah, you can repeat this on your own. And you can see this, we have the data over here that point number 3 and 5, that means the simulation is converged, but these two, they are not converged, yeah, due to whatever reasons. So it could be because it may need like a longer simulation time, or maybe it's just like simply not sufficient or not enough. It's not feasible, sorry. And then in real life, you also see this kind of data. So sometimes you don't have any data like this one, like these two. Sometimes you see this data, and then you have to make use of these data to make the model. Yeah, you could also say you could also do like, for example, you run it like I don't know, maybe 2 or 3 hours yeah, just to get a bunch of data, and then the next day you can also run it with the different variations as well, just to accumulate the data that you will use later on. Yeah, it's not necessary for you to run the whole entire simulation all at once. You can simply do what you can, maybe 2 or 3 hours per day, or maybe during the weekend, half a day or one day, or maybe the whole weekend, 48 hours, where nobody is in the lab. Up to you.
Yes, I would recommend to do like in the evening or in the weekend, So
Yeah, in the evening.
during the day, there sometimes there's a classroom, right?
Yeah.
So
And
they
then
might
make
disturb.
sure, even though that you're doing it in the evening or in the weekend, please inform the technician so that he knows, and then he may ask
Yes.
him to add to put this. We typically like put this paper, say do not disturb on this Yeah, hopefully nobody will
Yes, yes.
disturb you. But since you're three, I just realized it this morning when I was preparing for this. I realized that well, three of you are, I mean, four, all of you are working in industry in the plants, right? So you must have access to some data, and then that means your job is then to make the to make the block diagram so that you can present it so that other people can understand, and then you also understand what is happening in your plant, and then use that data to make a model, and then use that model to do optimization. So this whole work procedure that I'm now doing are exactly being done in practice, yeah, being done in practice, one way or the other. Um, so um, so that's why. So this is like a kind of like, if you don't know this approach before, that means it's a good learning point for you, so that you can then come back to your plan and then say to your boss that you can do this now, so you can optimize your plant or you can increase the performance of your plant. Yeah. Any other question? Yeah, I think regarding data that I think suggested, yeah, it's again, it's up to you how you want to do it. Either you get your own plant data, or you run this in the weekend on the in the night, and then you can accumulate the amount of data that you have, because it will then take some time. And then first of all, that you first have to understand how the plants behave, so how the simulation, how the process works. Um,
Zafran, may
yeah,
I take some announcement?
yeah, please. We are
So,
waiting for this. Yeah?
so this, so this is the regarding your test one. I think for this course there is only one test. So this is it. So the test is planned to be on next week on Saturday. So are you okay if we do in the morning 9:30? So the time duration is around 2 hours. It is an online test. 9:30 until 11:30. Everyone okay, or is there any objections or suggestion to put on another time, or you want to do in the evening also? But it is need to be to do at the same time. Although it's an open book test, but it's limited to 2 hours only. So any objections or other suggestion, please? Yeah, if you do have any objection, you still have time until maybe Monday or Tuesday maximums. You can suggest, and then we can ask the others if they would like to change the timing or the date. Otherwise, for now, the date is next week, Saturday, 9:30. And then in the afternoon is again the lecture, right, Zulfan? Next week?
Yeah, it's going to be yes or no. Yeah, we'll see. Because next week will be like this Deepal Valley holiday.
Yeah, it's a long weekend.
So I don't know if you guys celebrating this or have other plans already. Let me know. Otherwise, we'll then let's see. Yeah, because we also planning something. If that plan doesn't go, that means we'll have a class. We'll have the class as usual. Otherwise, we'll have to then postpone one class, and then you can have the whole Saturday for your. I mean, you can do the test on Saturday, and then that's it. Otherwise, the test in the morning and then another class in the afternoon. So I'll let you know. And you can also postpone.
Okay.
Any
So,
other questions, students?
okay.
It's I know that I'm being faster. I think it's also super fast because typically when I teach process simulation, it will take like a month or so, or a week. So it's not like 2 hours like this. It's even like less than 2 hours. 1 hour, I think, in this case, 1.5 hours. And then this also packed with the hydrocracking process itself. Um, but the idea is that in this project, the idea of this project is that so that you have the ability to do this on your own, like which data that you take, and then use the data to make model, and then use that model to do optimization using a very simple Excel solver, which I showed you already, um, and then try to make sense of the results. If the result makes some sense, and then you can then propose that. If not, and then check again the data, check again the simulation model, see if it makes sense, and see if it aligns with the knowledge that the people in the plant, in your plant, have. Yeah, um, for sure, make sure that it makes sense. So you can see now, yeah, it's still running. I think it's I don't know how it works. It doesn't work from the lowest to the highest somehow. You can see the kerosene. The higher the hydrogen to hydrocarbon ratio, means you put more hydrogen, you will get lower kerosene, but you will get more light distillate. Yeah, somehow, but you will then have to reboil more. So in the end, later on, if you can then put this into Excel and see how it behaves. It's like a linear or non-linear, and then we can see if this price is more expensive than this one, and then that extra price can then be used to cater for the additional reboiler duty that you are consuming. So that means it's worth a try to get more hydrogen into the system. But I also forget. I mean, well, it's just like an example for you, right? Because that hydrogen comes from the I mean, in this case it comes from the makeup as well. So this compressor, the power of this compressor needs to be taken into account to get like a more accurate results. But again, it's up to you whether you want to take that into account or not. Yeah, it's part of the energy consumption. It's just a matter that um, yeah, the more complete that you put into that you consider, the better it is. So it's solved. See, so I finished solving. So in 2 minutes remaining, I'll show you. I mean, yeah, I'll give you an example. I'll show you. Just you can just right click and then copy whole table. Yeah, copy whole table, and then you can then see Excel. Just to give you an example so that you know how to do it. So you can so you can see. So we have one independent variable, so you have to make sure, yeah, these and then the 3 dependent variables, and then you can say, for example, I want to see I don't know, so this one, okay, now which one is which? This is what I don't like, the automatic. Delete, and then I want to see the kerosene. Sorry. Okay. So so I want to see the kerosene. For example, yeah, kerosene. Make sure that you get the unit correct. This is then your X value, and this is then your Y value, the kerosene, and you can see. So it looks very strange over here, this guy. I don't know whether this is correct or not. Yeah. So you can see that the more hydrogen that you put in, the lower the kerosene production. And then you could also see it may or may not be like a straight line, but in this case you can, well, if you say, well, it looks straight line to me, so you could then say, well, linearly it goes like this. And then you can say, okay, now I want to display the equations. So then you will then use these equations. Yeah, or you can say no, it doesn't look like maybe it's a polynomial, so make it linear. So it's also not very good. So linear seems to be your somehow your best option for the time being. And then you can do the same for the diesel. And then this is then your data edit diesel, and then the flow rate is this guy. Nah, see, it goes up. And then you can do the same as well with the other guy, energy, and then select data. So this is just a simple example, yeah, for you. This is what. Okay, I don't like this. So this is divided by 1A. So now we have in megawatt. Select data. Okay. Nah. Okay. So now you have you have the equations roughly. So you say that between this and that, I see this as like a linear relationship, which you can argue. You can argue that this is all like a linear relationship from this point to that point. Yeah, this is what I mean. So from this point to that point, you can argue that this is like a linear relationship. So you can say that, for example, now if you say my I don't know. So what was it? Your x is then the what was it again? The hydrogen to hydrocarbon ratio, and this is then, for example, I don't know, 1200. And then your kerosene is now, in this case, you can use this correlation. So minus 5.5672 times this guy plus 50059. Can you see? It's very small. I hope you can see, yeah. Yeah. Okay. Just to give you an 40. Just to give you an example, yeah, you have to do it on your own. And then the diesel is 0.01 times plus. So this is valid. This is valid only along this range of operations. Yeah, energy. This is then okay. So now assume that you have a price. I don't know what your price is. I don't know. Just this. Take for example, this is then the price is then 10 is the price. And then this then maybe another I don't know, 3, and then this is then maybe 5. This is then maybe I don't know, this is 10. Make it like 2. This is also like a maybe 3.5. I don't know. Yeah, this is something that you have to find out. Something you can Google this yourself. So I want to say, for example, now. So this is then you have to do these calculations correctly. Yeah, I'll just give you an example. So this then your thingy, and then you can then say, okay, my sales would be this plus this, and your operating cost would be this. We have to do this calculation correctly, and then you can say, okay, now what is then my optimum x? Sorry, so this is your optimum x. You need to find this because this is just initial value. Okay, so you want to profit, for example, is then become your objective function. So this minus that one. So you want to maximize this guy, right? So you go to data, like we say the other day, solver, and then you want to maximize this guy, which is this one, maximize, and by changing which variable, which is then your independent variable, which is this one. So you change this, and remember that all of these are like a linear relationship. So you can then put like a simplex LP, and then it is then the minimum, or you have to put a constraint, yeah, because this is done before above 1100 and then below 1300. So you add the constraint, and then this one is below 1300, and it's also like above 1100. Okay, so this D26, and click solve, and then it will give you this one. So so it goes like, okay, so based on this price, so the optimum hydrogen to hydrocarbon ratio is about 1100. So it goes to the minimum. It goes to the minimum. It goes to the minimum. And then this is something that you have to think about whether this is it makes sense or not. Yeah. And then you can, yeah, you can do this a couple of times and then get more and more accurate the models, and then you can then test this, yeah. So you can later on, because you can do 4 6 so you can then compare. Okay, now, yeah, now you can then compare. You can have the optimizer. We don't have much time now, but I'll give you a glimpse now. Spend like another 4 minutes. So optimizer, so suppose now you have done your optimization in this. So this is then your simple plant model. So this is your simple plant model. Things that you can then play around. Yeah. And then we know that already, we set the base already, that this is then your plant, so to say. So once you get your calculations already done in Excel, and then you can propose this in to your plant. Yeah, you can propose this to your plant. So you use the same process calculator somewhere, tools. So you can use process calculator somewhere, and then to do the same calculations over here. To the same calculations. So you drag in, you copy and paste connection the hydrogen to hydrocarbon ratio, copy paste connection for the kerosene, diesel, energy, and so on and so forth, and then put in these numbers, the price for everything, and then calculate the operating cost in the spreadsheet. Yeah. So you do the same, and then you will then get the that the objective function. The solver over here is then this guy. So you know your objective functions, add, and then you know your manipulated variable, which is then in this case, this example case is then the hydrogen to hydrocarbon ratio only, and then the constraint is that your hydrogen to hydrocarbon ratio is then bigger than 1100, smaller than 1300, and then you can then click run and see if it gives you the same results. Yeah, so that's what I want to know. So what I want to know from your project is that your model, you can use this model, you know where to find it, or you can also you make your own model, or you can use your data, and then show me this the plant data that you make a surrogate model of this. So your plant data, so for example, this is my kerosene flow, my diesel flow, or maybe you make much more complicated or sophisticated, and then show me your prices, and then the assumptions why you get these prices, and then what is then the optimum independent variables that you get from this Excel, and then the results of this. Yeah, if you use this number, to here, that it gives you the same direction. Yeah, I want to see that as part of your project. Okay, so we have 1 minute. Do you have any question? Yeah, so silent means
Hi, Doctor. I am Swan here. Okay.
Yeah.
I have questions regarding the project. Which process or case study that do we need to do for a simulation, or just the hydrocracking that you?
Yeah, you can use this, because this is I think this is simple enough.
Okay, can.
You can just use this hydrocracking. You know where to find it, man. So we go to it's basically in you can when you instead of new, you can click open, and then you can see manual examples, and then reactors, and then this one. You can try to open the other process as well. It's also fine. Yeah, I mean, it's also fine. But in this example, I showed you this because simply it is hydrocracking, and then it is simple enough, and then it is related to refinery, really related to refinery. there are many other examples that you can select from. But make sure that before you do this case study, the sensitivity analysis, you understand the dependent variables that you want to control, and then the dependent variable that you want to see, and then the cost calculations. Yeah, just do some Google. So if you have any other information on the prices, that's also fine. And then calculate things, simple things like this. So you have the product sales, and you have the operating costs in this case. Here it's just very simple. It's just only reboiler, but you know for sure that hydrogen requires compressor, so that compressor energy has to be taken into account. And then what is then the optimum variables obtained from the optimization here, and then see if this number is also appear if you do the same optimization in this case in the plant, so to say. Or if you then if you have, like, for example, a base case, because your base case is the 1200, right? And then this case is also 1200, and then if you change it to 1100 in this case, what happens to the flow rate? For example, in this case, we'll take say if I change this, if I change this, so if I change this to 1100, what happens? It'll take some time. So you consider this as your plant, as a validation, as a validation of the this tool. Okay, because this is then your own tool now, the one that you can then use. No, you have to be patient.
I have another question.
Yeah.
So that if let's say I don't have the plant data, so that could I just use the Tapis oil data that you find from the ExxonMobil website as my project process input?
Sorry, say it again slowly.
Because I don't have the process data. So
you have the plant data.
I don't have the plant data.
You don't, or you have?
I don't have.
Oh, you don't have the plant. Okay.
Yeah. So that could I just use the plant data that you found from the ExxonMobil Tapis data as my process input?
You can, yeah. I mean, this you mean this is what you sorry, this is what you mean. Where is it? Where was it? Is this what you mean?
Yes.
Yeah, you can, because this is public knowledge. You saw me Googling that, yeah. So you can use this. You can use any data, but please make sure that you you know, right? So you understand. Make sure that you understand. That's more important for me. So you take it from here, and then this plant. So I mean, once you get this this flow sheet, you don't need to have any. I mean, you don't need to go through this, unless if you want to change this. Yeah, if you want to change this, and then yes, you can change this to the ExxonMobil data, and then see what happens. It can also be the case.
I think the easiest way is to use just this example, right? Because it's already there, the data for the essay, the oil data.
Yeah, up to you. I'm just giving you an example. It has this one. It takes quite some time because it has recycles. I mean, that is then the one way that we don't typically use this kind of software to do process optimization, because it will then take a lot of time.
Okay, so from our own data, I think you mean like it's not recommended to put recycle then? If for example we create our own data, for example, then in that one we don't need to put recycle to simplify the system or the case.
If you model your own plants, you mean?
Yes, like for example, we take the data from tapis, just the first example that you
No,
created.
the
If you use
data is
that one.
different from plants. Yeah, plant is plants, data is data. So this is your plant.
Mm-hmm.
This flowsheet is your plant, and then your plant will have recycles, which you can simplify or remove, or you have to have it. Like in this case, you have to have recycles because you have recycles in the heavy in the bottom, and you have recycles in the gas. So the two recycles over here. So this recycling is difficult. I mean, the more recycles that you have, the more difficult it is to converge, like you see in this case. Um, and then, but if you have your plant, or I mean, if you have your data already from your plant, somehow your plant, I don't know, you have your data. Yeah, your data is this.
I see. I got it. Yes, I understand.
Yeah, this is
Meaning
the
that
data.
if they have the data, they no need to go through all this symmetry
Yeah, you have the
simulation.
data, and you don't need to go to that symmetry because you have your plants already.
Ah,
And then you can just
okay.
from here, this is then your step 1, and then this is your step 2, and then this is your step 3.
Okay.
Yeah, and
All
then
right. Okay. Yeah. I think someone need to leave. I think it's okay. You may leave. Right.
yeah. Okay.
Mm.
I'm just, I don't know, waiting for this. But
Yeah, it's
any other
okay.
question? If not, then I don't think we want to wait for this to solve. But I guess at least I give you already what to do. If it's not clear, let me know. Ask in the group. Don't ask me personally. Ask in the group so that everybody knows. Okay. So thank you.